In this goal, we are going to be looking at real versus ideal gases. Recall PIVNERT, PV equals nRT, is called the ideal gas law. And most of our gas laws come from PV equals nRT. Let's look at Boyle's law. So at the beginning of the unit, we looked at Boyle's law, and he looked at pressure and volume, and when he multiplied their values, he got some sort of number. So in this example, we have 1 times 20. Our constant is 20. What would happen if I double the pressure? So now I'm at 2 atmospheres. Well, my constant still has to be 20. So my volume, because my pressure doubled, my volume would get cut in half. So I would have 10 liters. So that would maintain that 20 being the constant. And let's double the pressure again. Again, we're just revisiting this from before. And so doubling that pressure would again half it. And so I would have 5 liters. 4 times 5 is 20. Let's, for the sake of keeping our math easy, let's take the pressure all the way up to 10. So if we have 10 atmospheres pressure, what would we predict our volume to be? And you're thinking, well, 10 times what is 20? It must be 2. Our volume must be 2 liters. But when we go in the lab, we actually see that the volume is 0.8. And so that's kind of curious. All of a sudden, our gas law is not working. Let's double the pressure again from 10 to 20. And so again, we would think, okay, 20 times what gives me 20? We would predict a volume of 1 for our liters. But that is not what we see in the lab. Again, we see that our volume is 0.8. So what is happening here is under increased pressure, those gas molecules are getting closer and closer together. And when the pressure is really high, the volume's really low, and those molecules get right next to each other. And instead of having a gas, it gets turned into a liquid. And so that's what's happening here with this breakdown of Boyle's law. So when my pressure is lower or my volume is bigger, it remains a gas. But as soon as you have a high pressure or a small volume, you have turned it into a liquid. So this is one of the things that we can see, the difference between a real and an ideal gas. An ideal gas means that you do the math and it works out perfectly. But in the lab, we see that we can't go down to really, really small volumes and have them stay a gas. We see that they turn into liquids. And so real gases don't always follow the gas laws. So you might think, well, if I can't ever use the gas laws, then maybe we should throw them all out. No, 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 no. We want to keep our gases behaving like gases. And if we do that, then we can use the gas laws. So let's go to this next slide. So let's look at the difference between a real gas and an ideal gas. So real gases, there's lots of examples. So the oxygen gas we're breathing, the CO2 gas we're breathing out, we have hydrogen gas. Real gases take up mass. I can look on the periodic table and calculate their masses by adding up their molar masses for each of the elements to find the mass of a gaseous compound. They also take up space. So that means that their little atoms or their molecules, they are taking up space. And there is some intermolecular forces or van der Waals forces. So this is the London dispersion forces or the dipole-dipole or hydrogen bonding if you have something like water vapor. So you do have some intermolecular forces that are there. And gases, they do follow collision theory, meaning that they'll travel in a straight line until they hit something, either the sides of the container exerting a pressure or if they hit another molecule. And we do assume that the collisions are elastic, meaning that no energy is lost in that collision. So let's look at the characteristics of an ideal gas. And I've listed 5 characteristics here. So what are some examples? So first of all, they are imaginary. So that is a characteristic. So there's no ideal gases. There's no examples to give you. They are described as having what's called a point mass, meaning they have a mass, the mass that's on the periodic table, but this particle takes up no space. So that's the point mass. Has a mass, but takes up no space. So again, they are imaginary. And these truly have no intermolecular forces. So you can put them in a really, really small container under a lot of pressure and it will stay a gas. So, and obviously we're talking about something that's theoretical. So something that we can think about and it works great on paper. But when we go back in the lab, we have to contend with real gases, how they do have intermolecular forces and they do take up part of that volume that that you put them in, meaning that their molecules take up some of the available space to move. So the most important thing on this slide is in this yellow box. So how we can use our gas laws is we can make sure that real gases behave like ideal gases, and we do this by having a very, very large volume or a low pressure. So that way the molecules have plenty of room to move around and they're not going to get so crowded that they might turn into a liquid. Also, we want to keep their collisions as elastic as possible, and we do that by having them have a high temperature. So when they collide with a lot of energy with this high temperature, they are able to have more of an elastic collision. So they'll hit each other and bounce off, or they'll hit the wall of the container and bounce off. So these are the two important ways to keep a real gas behaving as an ideal gas. So having a low pressure and a high temperature. So let's look and see what happens if we have the opposite of that. So I'm just going to go to this X right here. So I'm in the gas area of this phase diagram. Let's lower the temperature and see what happens. So if I lower the temperature, the molecules are moving slower and slower and slower. And eventually I'm going to cross that liquid gas equilibrium line. And I'm not going to be dealing with a gas anymore. I'm going to be dealing with a liquid. And you can't apply the gas laws to a liquid. So as a result, we want to keep the temperature high. So we want to keep it behaving as a gas. So this is a phase diagram for water. So if we want water vapor to behave as a gas, we want to make sure that at standard pressure, we're going to be above 100 degrees. So temperature is going to help it keep in that gaseous phase. We also can look at pressure. So if I increase my pressure, so I go up, 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 eventually I will cross that liquid gas line. I'm going to draw it a little bit straighter, see if I can do a better job this time. Well, I don't know, not so much better, but the point is if you put it under a lot of pressure or a small volume, you're going to turn into a liquid. And again, you can't apply your ideal gas laws to liquids. So we want to keep gases behaving like gases. Let's talk a little bit more about real gases and their intermolecular forces. So on this diagram, it's to show a picture representation of an ideal gas versus a real gas. So this right here is a real gas. So it takes up space, so the molecules are taking up part of that volume, and you can see it right here in this little green square. If you were to smush them all in a corner, you would see that not all the volume is available for the atoms to move. Some of the volume does get used up with the atoms or the molecules, the space that they take up. Okay. So as a result, when we do look at the volume and we try to predict the volume, for real gases, the volume is more than predicted. Let's look at an ideal gas in this situation. In an ideal gas situation, so you'd have your molecules, and if you were to try to condense them down, remember in an ideal gas, you're not going to have any volume. So it's essentially empty. So again, ideal gases are imaginary. Let's look at intermolecular forces. So I have my ideal gas here. And so you can see that they're hitting each other, but there's no forces in between the molecules. While here are my real gases in both these situations. So in this first one, you see that when the atoms collide with each other, just because they're close to each other, those van der Waals forces, the dipole-dipole, the London dispersion, they kind of kick in just a little bit. So the collisions aren't as elastic. So obviously the faster they're hitting each other, then the more like elastic collisions they are, but they do kind of sort of get sticky when they're hitting each other. So again, if we keep the temperature really high and keep the volume really large or the pressure low, then we are going to minimize those. Let's look at this next set. So this is showing how it hits the side of a container. So your ideal gas will just hit the side of a container with the full force. But when you look at a real gas hitting the side of the container, as it goes to hit the wall, the molecules that are around it kind of grab it. and those intermolecular forces are there. So it's kind of like it holds it back a little bit. So as a result, it doesn't hit the side of the container with as much force as you would predict. And so the pressure for this real gas is less than predicted. And that's because of those intermolecular forces. So intermolecular forces are very, very important. It's not like we want to wish them away. If we didn't have intermolecular forces, we would never have liquids. We would never have solids. So we need these intermolecular forces. So it's just that gases being so far away, if your volume is large, that intermolecular force is minimized. So it has to do with location. So as they're close, it's a little bit sticky, but then as they pull themselves apart because they hit each other with such force, then those intermolecular forces go away. So this concludes ideal gases versus real gases. Again, you want real gases to behave like ideal gases by having a high volume or a low pressure and having your temperature high. You want to keep those gases in the gas phase.